Cool. So welcome to NASA's Best Students. Afternoon, everybody. I know I've probably seen the elementary guys before. I think we did We Do together last year, right? Red. We're going to do something a bit different this time around. So my team is called NASA's Best Students. We, just like everything at NASA, it's an acronym, beginning engineering, science, and technology. And we are based at the University of Maryland, Baltimore County. But we're funded by NASA, which means we get to do cool NASA stuff, and we have twice the bureaucracy. Yay! No, honestly, I love my job. I love the team we've got. It's pretty fantastic. The first 20 minutes are going to be what I hate doing, which is me kind of talking at you a little bit. But then we'll actually dive in to do stuff because that's way more interesting, and that's what you guys are here for. Any questions before we start? Cool. So just so you know, my name's Catherine. I'm an instructional designer with NASA's Best Students. My own background is actually undergrad in mathematics, and then I tried teaching in high school for a year. I don't know how you guys do it. Kudos to you. Seriously, I have utmost respect for all classroom teachers, because what you guys go through day in and day out is amazing. So I actually took a different path, and I went into informal education. So my master's is actually museum education, of all things. And I work a lot with after-school, weekend, evening programs. That's going to form the basis of my dissertation if it doesn't eat me first. Anyway, so if I get totally incoherent and loopy at any time, my bad. I'm writing my dissertation, that's my excuse. But just yell out, hey Catherine, I can't hear you, or you're being really weird, or what the hell is going on in here, it's crazy. Just yell, I'm not going to be offended. Just, you gotta let me know when things are going a little off the rails a bit. But in the meantime, we're NASA, so we gotta show some pretty cool videos. By the way, I apologize for the projector quality. It's gonna look like you've got 4 tequila shots in, goggles on. We can't get it to focus, I don't know why, but mercifully, it's not that important. But we've got a video. So it's just fun to get started with happy, bouncy music. That's as far as I'm concerned. But basically what our team does is we have engineering curriculum. Even though, outside of Massachusetts, engineering isn't necessarily really taught in school, we think it definitely supports everything that you folks do in math and science. And we're taking it from the perspective of kids are natural engineers. They want to problem solve. They want to go and figure out how things work. So let's take advantage of it. In particular, we want to start, that is way more focused than it was before. Sweet. Sorry. It was really bad this morning. It looked like everybody was hungover. It was awful. I'm sorry. But yeah, kids are natural engineers. We want to get them early when they're really naturally at it, and we want to keep them going. That's also where the research is supporting for underrepresented kids in STEM, girls and minorities. We really need to kind of have that constant ongoing contact with the kids so that we don't lose them in middle school and high school. There's also selfishly NASA needs engineers. Anybody know the average age of engineers at NASA 40 some years ago when we landed on the moon?
Late 20s.
Late 20s. Anybody got to guess what it is around now? It's pushing the 50s, yeah. So what does that tell us about the engineering workforce at NASA? It's
opportunity.
It's a stable opportunity, well, for a while, because what's going to happen in another 10 years or so? They're all going to retire, which means what for NASA?
Big job boom.
Hopefully there's going to be a big job boom for our young folks, but it means that NASA's definitely going to be needing to hire some people, and that's where you come in, because you guys are the inspiration and the trainers of the next generation of scientists and engineers and mathematicians. And you know, NASA's never going to run out of universe to discover or to work on, which I think is, it's a pretty big deal. What you guys do is hopefully inspire kids to go on and take on these challenges. If nothing else, even if we don't get them into those STEM careers, we want some more STEM literacy in the world, right? We're tired of all of these kind of scary news articles of people twisting findings on research, and we don't need any more of that. So, I'm preaching to the choir here. I don't need to tell you there's basic, you know, all of the scare, everything about how we're failing our kids in STEM. What we're trying to do really is institute cultural change here. We want it to be cool to be smart. We want it to be cool to work hard and try learning new things that, you know, we haven't done yet so far. And lately, with the kind of big national push towards more STEM education, we're starting to see that, but there's still a long way to go. And again, that's where you folks come in, and it's so exciting to see you guys kind of bridge both teaching practice as well as the content, because I think that's really where we're gonna best suit the needs of our kids. So just a little shameless plug, our group has hands-on engineering curriculum. It's more applicable to the elementary than the high school, because our engineering curriculum goes K through 8, but it's hands-on project-based learning, and it's different design challenges to get kids into engineering. For high school, we have robotics, and robotics takes a couple forms. The downside to doing robotics is it's really expensive, right? Really expensive. We do two kinds. We do stuff with Lego. The elementary teachers got our We Do curriculum last year, but we do Mindstorms for middle and high. And we also do Arduino-based robotics, where we teach the kids actually how to wire the breadboard and write their codes and all of that stuff. I'm still amazed we survived it. Our pilot test was with 100 sixth graders at the same time for 5.5 hours on a Saturday. And someone thought it was brilliant to give them chairs with wheels on them. Yeah, it was a long day. And glue guns, right? We had wheelie chairs and glue guns, and it's like, this is the greatest day ever, right? Anyway, I say this as potential future avenues. If, in case you're interested, I can talk with you more about it. But you're here to do stuff, right? I hope. I know it's after lunch and we're getting a little sluggish. It is humid up here, right? Yeah. So we need to. I was hoping it was going to break last night with the rain, but alas. Anyway, so our exercise today is going to be deceptively simple. We're going to do it, and you're going to be like, this is way too easy. What's the point? And it is meant as an introduction. And the reason we're doing it is there's a very high value payoff for the little amount of work we're actually going to be doing. So all I ask is that you just kind of bear with me. Hopefully I'm a trustworthy enough person that you can stick with me for a little while. But any questions or thoughts or anything before we get started? Cool. Am I talking loud enough, by the way? Because I've got this right here, so I'm not really sure. Anyway, so what we're doing is measurement basics. And we'll get into it. But the very first thing is we've got about, I think, 32 people in this room, I counted. So I'm going to ask that we divide up into 5 teams, either 6 or 7 people per team. Good? It'll probably be best to keep elementary with elementary and high school with high school, but it's totally up to you if you wanted to mix that up. But feel free, rearrange chairs, whatever. Once you've gotten to your groups, I'll explain how we'll be doing this.
My stuff today, and then
Five groups, please. 5 groups of 6 or 7 people per group. 5 groups. 5 groups. Counting's going to be important, folks. 5 groups of 6 or 7 people per group. If you have more than 7 people per group, I'm going to ask you to redistribute. I'm talking to you folks in the corner. Thank you.
Yeah, but what do you mean?
bill me. Send it to me.
Six, 7. All right, we good? Awesome. So, in a moment, I'm going to be assigning each team an object. You will be asked to measure the perimeter of this object. However, I'm not going to give you rulers. Rulers are boring. I'm going to ask that everyone in the group measures this object with their hands. Now, I'm being intentionally vague about this. You can choose however you would like to measure it. But each person in the group, whether it's 6 or 7 people per group, has to measure the object with their hands. So each group should have 6 or 7 different data points. Questions? All right. Team number 1 over there, you're going to get the periodic table. Team number 2, you're going to get this table. Team number 3, you're going to get the perimeter of the lectern, the side that's facing you. Team number 4 and team number 5 are each going to get a giant cardboard box.
So to restate, we're going to measure the perimeter of our object.
Yes. Yes.
Each person is going to measure using their hand.
Correct. Each person in the group is going to measure your object using just your hands. It'll start to make sense after we get through this first iteration. That is, I left it intentionally vague. However you choose to measure with your hands, that's how you can do it. Yeah, so go ahead, add those up. Team number 2, have you made your measurements?
Yeah.
Read them off to me.
Oh, 54.
Say it again.
54. 50. 53. 55.5.
And what?
47.
Team number 3, do you have your numbers?
Yeah. Give the exact 23 number. 23 and 2/3.
23 and 2/3?
22. 22. 24. 22 and 22. 24 and 22.
All right. Team number 4 in the back corner, do you have total number hands? Read them out.
16. 16 and a half. Another 16.
All right. Team number 5, give me your numbers.
Wait a minute. Hold on. I'm sorry. One second.
We're still calculating.
All right.
Exactly.
I'm doing it. I'm not doing this. Right? We did the river.
8. All right, keep working. Let me go back to team number 1. Team number 1, what are our numbers?
66.8.
Second one?
52.
Wait, what?
That's third thing, second, yeah. Then 52.4. 61.6. And 70.
We have our group 4. You want to arrange in our...
No, because I'm actually going to get those in a minute. Team 5, have we made our calculations yet?
Yeah.
All right, read them off.
16, 17, 19.
Hold on. 16, 17, 16,
19,
19.
18, 19.
All right. So are these meaningful at all? Why not? I don't know. How do you derive meaning from them? You could average stuff, but that's not really going to help you. So I'm going to hand out rulers. However, you are not to measure your object with the ruler. The way we're going to do this is you're going to measure your hand. That's going to be the number in column 2, hand size. Centimeters, by the way, we're NASA engineers, we use centimeters. Huh? Bless you. Yeah, no, we're not doing millimeters, we're doing centimeters, right? So you're going to measure hand size in centimeters. And then your total perimeter for column 3 is going to be column 1 times column 2. And column 3, that's what I want your average in range for. Sound good? All right. I've got 2 rulers per team, so hopefully that'll speed things up.
Are you writing it down twice?
Whoops.
Claire, what are we doing?
You're going to measure your hand in centimeters.
Does it have to be a certain way or the way you measure it?
Oh, should we did it?
You measure it.
The way we're using it.
This is NASA, you can't ask
I'm
questions.
just saying if you're doing like this.
So, given that the object is to get to the perimeter of what you're doing, which way should you measure your hand? What you used, yeah. Oh, sorry.
Here, yeah, I mean that's what I do too. But look, if you go,
By the way, out of curiosity, how does one measure 0.8 of a hand?
Every finger's a 0.2.
All right. That makes sense. The 2/3 actually. How'd you do 2/3? Less a knuckle. All right, I can see that. I can see that. All right. Someone at the last class came up with a 5/6, and I'm like, I don't even know.
That's what we were going to do.
He was 4.5. This was Scott. He was 7 by 5. That's 7 by 5. Yeah. Measurement.
So once you've got that measurement, go ahead and do the multiplication so you get your total perimeter in centimeters.
My problem is I feel like
It should be that.
If I see people whipping with the rulers, I'm gonna have to take them all away.
Right, what was your additional 14 and a
Group 1, do we have our numbers? Still calculating? All right, group 2, do you have your numbers? You ready? You ready?
Yes.
All right, give me perimeter.
351. 405. 424. 416.25. 406. And 368.
And what was your average?
395.
And your range?
73.
All right, team 1, you guys ready? All right, give me your perimeters.
619.8. 668. 634.6. 585.2 and 644.
And average?
630.
And range.
Oh, I didn't do range. Sorry.
All right, come back to me.
644 or no 668 is my highest. You want like the difference between the highest?
Yeah, give me the difference. 585.2 is your lowest.
82.8.
All right, team number 3, give me your perimeters.
437. 437. 441.32.
Point what?
32. 407. 432. 418. 385.
And your average? 420. And your range? Should be 441.32 minus 385. All right, team 4, do you have your perimeters ready? Read them off to me. Just the perimeters, yeah.
313.5.
And your average?
305.56.
No, which, oh, I'm number 4. So
And your range?
I got 407.
And team number 5, what are your perimeters?
288, 306, 280, 399, 313.5, 324, 323,
And your average?
319, and 111.
All right, so we've got quite a bit of variance up in here. So what happened?
Well, when you're using a unit of measurement, which is your hand, and then you don't have one hole, you're estimating if it's a half or a quarter.
Yep. So first thing I want to point out, this has happened in both classes so far, and now this one too. For those folks who had whole numbers, nope, that didn't happen. For those of you who had accuracy to 1 decimal point, how did you end up with something to 2 decimal points?
Wait, what? What was it?
Because you're multiplying.
If we started off with, there we go, 18, there's a whole number. How did we get to 2 decimal points in the perimeter? This is not a public shaming thing. This is a point that,
Like you're multiplying a decimal times a decimal, so.
but we don't have a decimal. We have 18. That's a whole number.
Yeah, but but some of them have decimal.
Some of them have 1 decimal, but how do they get to 2?
Oh, I didn't give them to the same order.
That, all right. My point is that this is, even though it seems very introductory, it's a way for you to address the ideas of precision and accuracy with your students, right? Because you can talk about how when you average a bunch of numbers together, you need to have the same levels of precision, right? That's my point here. That's why I pointed out. Anyway, what I would like you to do is take a couple minutes and in your groups come up with why, a couple reasons why our numbers are so all over the place. By the way, you need to be a little more specific than human error for what it's worth, right? Human error is great, but we need to know exactly what happened. All right, so safe space, no wrong answers, just kind of talk it over with your team. What are some reasons behind some of the crazy?
Also, I mean, if you look at our data,
You judge the starting point. Like, I think you can say that it's going to be where's the end of your column.
You didn't say where we were in. What are we doing?
Were you able to let more full? Yeah. Dropped it all, and you were contorting yourself.
Yep.
You're familiar with the Marshmallow Challenge. I think you guys presented that to us maybe last year.
Possibly.
It was like you give the kids marshmallow, spaghetti, tape, string, and they have to build a big tower.
Okay, yeah.
It's just a real quick, like, super easy, like, one-day quick lesson.
Mm-hmm.
Do you have any other, like, STEM challenges that aren't super drawn out that you do with any of your groups?
We do the curriculum that we have online, the design challenges, you know, Mars rover, stuff like that.
But nothing just like kind of like one like 30-minute type of activities.
What you can do is NASA has, if you do a Google search, NASA Rocket Educator Guide, they have specs on how to make a PVC rocket launcher.
Oh yeah, I do all of it. Yeah, I've been in it for 5 years, so I've seen a lot of the stuff. And last year when they presented that to us, it was like the first kind of like start thinking, like working as a group, thinking as a group, think outside the box type of thing that I really enjoyed. I do it with my kids on the first day. I teach high school chemistry, so it's just kind of like totally outside the box. I was looking for more of those, like just like when you have like a little bit of time to fill, or you want to break away from the curriculum, like just getting them to think about STEM, because I'm afraid too often people just think STEM, science, technology, math, and they see them as separate entities. I want to try to get the kids to focus on that, so I was just curious.
So the Museum of Science in Boston does a lot of engineering design challenges that are meant to be in kind of, you know, a quick, easy kind
what's
of.
it called?
The Museum of Science in Boston. Their website is mos.org.
Okay. Science Boston. Okay.
And some of the ones that, because I actually used to intern for them, and so some of their challenges were, can you build a tower to support a baseball, tennis ball, bowling ball at a newspaper?
That's what I'm looking for, that type of stuff.
And you know, hopefully the kids get, you know, just newspaper and tape, and eventually they get to the fact that if you roll the newspaper, it's going to be strong enough. And you set the challenge that, you know, can you build a tower this high that will support a bowling ball?
Okay.
Things like that. They did like catapults, if you really want to make a mess, where you just have a cotton ball. And they can, if they want to tape the cotton ball down and spoon and a ruler, and you just start flinging them and see if they can get it farther and farther. And
Okay, great. Thanks.
sure. All right, folks, we got some thoughts. So why is our data all over the place? Because everybody measured all over the place. Yes, well.
We were discussing how maybe our hands might have been flat, cupped. We didn't discuss where the beginning of your hand or the ending to measure end to end.
All right, so there might have been some inconsistencies as far as measuring the hands. But keep in mind, we did that second column to try and eliminate that issue, right? Hand placement might be a factor, but again, you know, you theoretically, if you measured side to side, then the measurement you did for column 2 would have also been side to side as opposed to like up and down or something, right? So again, that should have hopefully standardized things. What else?
Different size hands.
Different size hands, but again, we standardized for that in the second measurement. Yeah?
We estimated a quarter, a half, and 3/4.
All right, estimations are going to start getting into it, right? We got a lot of decimal point things up there, which again, that's why I was asking, how are you finding, you know, 2/3 of a hand? What does that mean? Right? So estimation's fine, but if you look at it, our ranges are, you know, close to a meter divergent.
When she said about hand placement, it's not just hand placement of measuring across the ruler, it's a hand placement on the object. Like our hands aren't always flat, we're bent up little things, or we bend them other ways, and we're not always measuring straight across the same distance there. So there's not a consistency.
All right, so even within one person, you're not necessarily being uniform. Excellent, yeah?
We didn't have a procedure, so half of our group measured around like every single like hand placement around the whole table, and then half our group did length and width and multiplied by 2. So I think like we would have maybe been more consistent if we really refined that.
All right, and what's the potential peril to just doing half of it and multiplying by 2? Well, it's also, you know, if you're making an error in your initial measurement, you're gonna then magnify that issue.
But I have to say, like, if we got 12 hands of range in our original. That's one side of the table. I mean, like, I would have gone back and made them do it again. My students, I'd be like, listen, that's like a whole side of the table. Like,
Rotate everybody's hand.
Right. What else? Yeah?
What we should have done.
What should you have done?
Each person like lines up and goes one hand over the other, and that way we pretty consistent flow.
So you're averaging the hands.
So you're automatically averaging the hands.
Right, but the whole point of this was to get multiple data points, and also the reason I bring this is because, again, as simple as this may be, this is rich for opportunity, especially for the high school folks. You can get into data analysis. You can talk about means, standard deviation, all that good statistical analysis if you choose. Right? We had one group in one of the earlier sessions, they had a group of 5, and they said, well, if you drop the lowest and the highest, they're really, really close together. And it's like, yeah, but you're left with 3 data points. So what's that telling you? Not a whole lot. Is this good enough? What is good enough?
You should find it within one hand, right?
Within one hand, that's ambitious. What's good enough? When are you going to be happy that you have a good measurement of your object? Do it several times. All right. All right, so if you look at your sheet, there's a little line in between the 2 charts that says Saving Tom Hanks. And we have that there as a kind of mental break because, there's the phrase, it's close enough for government work. That's all fine and good, but when you're talking about putting humans in space and on another planet, close enough isn't good enough. Right? So I bring this up because, New Horizons, we launched it to Pluto, it went 3 billion miles away. And you think, 3 billion miles away, a centimeter doesn't make that much of a difference. Well, depending on where you lose that centimeter, it potentially really, really could. Right? So I've got a clip from easily one of my favorite movies ever because I'm a total space nerd. I am. I'm a total space nerd. It is what it is. I've accepted this a long time ago. Anyway, I bring this up as kind of a little mental break, and we'll talk about how maybe why we need to be a little better in our measurements. So if you bear with me a moment. All right. Can everybody see that, more or less? Approximately?
We have a situation growing with carbon dioxide.
There's a CO2 filter form on the lunar module.
5 filters on the lane.
Looking good for 2 guys for a day and a half.
So I told the doctor,
They're already up to 800 inches. Anything over 15, your judgment blackouts, the beginnings of brain asphyxia.
By the scrubbers on the command module, we take square cartridges.
the ones on the limb around.
Tell me this isn't a government operation.
It just isn't a contingency. We don't know what we have to do.
The CO2 levels have been getting toxic.
Well, I suggest you gentlemen ventilate with a square peg in a round hole.
Okay, people, listen up. You come upstairs, Kansas is this one, and we gotta come through. We gotta find a way to make this fit into the hole for this, using nothing but that. Let's get it organized.
Okay, let's build a filter.
Get some coffee going too.
So I bring that up because, for that scene in particular, because if I asked you to get a more accurate measure of your object, what's your first instinct to tell me? What do you need? A ruler. Well, what if you don't have a ruler?
Something that's not
Something a little more standardized. That's why we did that measurement, right? So as you've probably guessed, we're going to try this again. This time it's life or death, right? If we don't get, what's an acceptable range to you folks for this kind of activity?
0 tolerance.
0 tolerance. I think that is exceptionally ambitious. If we said, who said 1 hand before, right? So we're talking what?
7 centimeters.
All right, let's say 10. You think you can get your range within 10 centimeters? 15, 20. All right, so anything more than 20 centimeters and we've killed the astronauts. All right, I will be taking your rulers away. No cheating. We're going to do the same exact thing. You got to do hands first, and then we'll standardize it. Questions? I suggest you start strategizing. All right, team number 2. Do you have your average ready?
Yeah, what's our
Give me your average.
is 393.7.
And your range.
24.25.
Team number 3, do you guys have your average yet?
We do.
432.8. And our range.
Working on that right
Minus 62.5. Excellent.
Oh my God.
Team 4, what's our average? Average? All right, team 5, do you guys have your average? Still working? Okay.
You want the range first?
Average and range.
295.58. And the range is 32.
Oh my God, that's first number.
Interesting. I'm a scientist. I find most things interesting. You guys ready? Yeah, average and range, please.
Our average was 639.33.
And range.
16.00.
That is something.
How many times did you guys actually measure and count?
Multiple. Over and over again. You're like, really? That seems like a lot different. Try it again. Okay. Our average is 305.63. Our range is 42.63.
Sorry about that. All right, so we had some improvement. We had one team actually do worse. Good job, guys. That's not unusual.
Yeah.
We had one team within our potential error range of under 20. Only one. So, what happened here?
We were more meticulous.
More meticulous. Explain.
We standardized our hand.
Standardize your hands more. So what did you do?
Thumb off.
Cut your thumb off. All right. That seems a little barbaric.
Some people's thumbs go like that. All that.
All right.
Going across moves the rows of the periodic table so we can try to get it more
Rather than
in a
trying to
straight
reach all
line
the way to
going
the top.
All right. So instead of trying to reach out of someone's arm reach, and also to avoid I'm assuming to avoid some of the curvature issues, right? Because it's not totally straight across the top. All right. So standardizing of hands. What else?
We did use the paper. And then folded it into eighths so we could, because you're still doing some estimation. So this way we could be a little bit more accurate with it.
All right. All right. What else?
We measured
Yeah.
the same distances multiple times.
Okay, so we did multiple data collection. All right, yeah.
We clarified the procedure, like we measured on the sides, and the knuckles.
Clarifying your procedure and consistency is a big part of it. What else? So what's the real perimeter? How would you find out? Is that the real perimeter, measuring with a ruler? You sure? You really sure?
Do you have lasers?
We don't have lasers. So the reason I'm kind of asking and joking about it is when I said that there was a big payoff to this, and that is all measurement is going to be uncertain, right? Even with your ruler, because let's say you had a meter stick and a ruler. Are you going to get the same results? No, why not? Why might they be? They're made by humans, all right. So there's always going to be human error, right?
And material error.
All right, so it's a poor craftsman who blames his tools, right?
Well, the wood can expand and contract.
All right, these are brand new rulers. I think you saw me unwrap them.
The accuracy, they could have been sitting in the car.
They could have been sitting in the car. All right.
You ever see a Shrinky Dink?
I'm so sleep deprived. All right. So, but really, even if you were to measure it with a ruler, is that really a good measurement of what the perimeter is? Why is it more reliable than hands? But, okay, so placement issues, right? That's what a lot of people kind of came back to, placement issues. You still have to keep moving the ruler along. You're still going to have a placement issue with this.
So fewer placement issues with that, and fewer still with like a meter.
Bless you. All right, so you're going to have fewer placement issues, bless you, with the meter stick. Are you going to have as fine accuracy with the meter stick? The ruler goes down to millimeters.
And it's flexible, it goes around.
Not all of them.
Plus, there's more room for error.
So again, this is where we're trying to come to, is that even with the ruler, your measurement is, there's still going to be a degree of uncertainty. This is a really, really powerful thing for science as far as I'm concerned. A lot of people are still kind of stuck in the rut that, STEM is all about one right answer, one right way of doing stuff. I've actually butted heads with my parents. So my parents met at an engineering conference. My sister and I didn't have a chance, right? So I majored in math in college, and I also minored in literature, which it still breaks my parents. Like they can't fathom it, because my dad's like, but how can you deal with the literature courses? They're so subjective, and in math and science there's one right answer, and you know how to do stuff. And it's like, well, that's not actual math and science then, because the whole point of what we're trying to do here is recognize that for any given problem, you have multiple different approaches, you have multiple potential different solutions, and the methods by which you do so, bless you, are potentially going to change. So what we're trying to do with NASA's BEST and with a lot of what we do at NASA is recognize that, yes, you guys have your learning standards to deal with, and someone actually in the last class who did AP Physics said there's a whole big new standard in AP Physics all about measurement and uncertainty and things like that. We're also trying to get at those kind of soft skills. We want kids to communicate better. We want better critical thinking. We want to recognize that, failure is an option, and and it's a valuable one at that, because you're going to learn from it, right? So you could do this. We could keep, if we had the time, we could keep going and going and going. And you think we're going to get any better? Probably not. Even though there were a lot of teams that improved this iteration, if we were to do it again, we probably would have at least another team get worse again. Because, there's going to be, unless you're really worse the first time. Unless you're so bad the first time that there's only improvement. There's an argument to be made for that, I suppose. That's not what we're striving for. So someone mentioned, the first time around looking just at the number of hands, you wouldn't let the kids go on because, they're like a table length off. Well, again, that's what we're trying to get at here, is through a silly exercise. I mean, like I said, this was going to be simple. We're measuring stuff with our hands, but hopefully you can see that this potentially opens up a number of different ways where you can address really, pretty complex topics with your students. I mean, if you really want to get philosophical, you can get into the meaning of truth and all sorts of stuff like that, but that's a little too touchy-feely for me. When do you ultimately find out the actual measurement? You never do. I mean, you can go ahead and measure your object with the rulers, that's fine, but I mean, that's not really the point here.
that's not an actual measurement anyway.
Thank you. That's where we're going, right? Because everywhere we can keep making more and more fine rulers, and we can measure things with lasers, but there's still always going to be some degree of uncertainty with the equipment that you're using. That's
Tolerance.
there you go. So you can talk about tolerance and error measurements and things like that.
You identified an error tolerance of 20 centimeters, right?
But is that good enough?
Well, that's what was identified. Is that
Well, that's what we identified, but you know, we could also it was also kind of an arbitrary decision. I mean, we could have made it 2 hands or something like that. But anyway, yeah, the whole point is that for any measurement, you're going to have that degree of tolerance, and whether or not you're okay with bumping up the edges of that degrees of tolerance. You know, if you have an allowance of up to 20 centimeters and you hit that range of 20 centimeters, is that really okay?
is there an example that instead of that, is there an example you give your kids, like you're talking about a centimeter? Is there an example that you can give that if there is an issue all 5 that operations is failure, and then
I'm sure there are. I don't know any off the top of my head, but one example I like to use is during the Apollo missions, the engineers didn't trust the astronauts to be able to land the lunar module, right? Because engineers, there's a certain arrogance to engineering, right? And so they didn't want to leave it in the hands of human error. And so when Neil and Buzz were taking down the Eagle for the landing, the autopilot was taking them into a field of rocks. And so Neil Armstrong actually had to override the autopilot. And it actually got so dicey. They had 90 seconds of fuel left, or they would have had to abort the mission. And so if you actually listen to the radio when they landed, you know, they land and Neil is like, you know, Houston, Tranquility Base, here the Eagle has landed. The response comes back from Houston that's great. You've got a room full of guys about to turn blue because they were this close to missing the moon because the autopilot was taking them into rocks and Neil had to fly over to make sure they landed properly. So I don't know if there's a specific example off the top of my head that if you miss it 1 centimeter at one end, the repercussions down the line, but I'm sure there's a lot of stuff you can think of.
What was it, satellite telescope that they didn't convert the centimeters?
Yeah, there was a mission in 1999 where the design team, it was supposed to land on Mars. The design team, I believe, used metric. The build team, I believe, used imperial units. So that's, you know, when you're talking a meter and a yard, it's roughly close enough, right? Instead of landing on the planet, it smacked right into it. We lost millions of dollars on that one. Yeah. Yep, it's a great way to talk about standardization of units and making sure everybody's consistent. Any questions before I let you folks go?
Policy change after that mission?
Was there a policy change after the mission? I don't know off the top of my head. I know that standard practice is really to use metric in the STEM fields, so I'm assuming it was something like that. Thanks, folks. I think this is the last time I see the elementary guys. Sorry about that, but I think I see the high school folks tomorrow. Thank you. Have a great Thursday. All right. If you're coming back Thursday, then you'll see my colleague Lori. Cool. Have a great. Do whatever. I don't really care, to be honest. I'll take the rulers back. Yeah. Thank you, folks. Have a great rest of your day.